Welcome back. Let's talk about this argument validator lab. What I'm asking you to do is write a program that determines whether an argument is valid or not. So make sure you've looked at the previous videos where I've explained what is the formal structure of a symbolic argument, and I've talked about what the rules are for determining validity of a symbolic argument. So make sure you've looked at those previous videos. So the best way to explain this is actually to get into the source code that I've posted, and we'll do that in a minute, but let's go through this handout first. So down in here I've got 6 arguments that I want you to check for validity. And see, it turns out the first one, this argument 1 here, it's going to be invalid. And then the others, I'm not going to tell you right now, but I want you to run the program and determine if these arguments are valid for all 6 of these guys. So let's see, the first one here has a compound proposition P1, which breaks up into this statement P or Q. And then the second compound proposition P2 is just the small statement P, and then the conclusion Q is the small statement, a little q. So here we're doing an or, okay, and then here we're doing implication over on this guy, and then here we're doing, I think this is because, and here we're doing maybe, which are logical operations that I've just made up. So you need to implement those logical operations first, and that's what I'm showing in this table. Now this was in a previous homework, implementing these functions for logical operations. So that should be done already if you did the previous homework. Now let's get into the source code that I've posted, argument CPP. So I've got this pulled up already right here. So let's kind of go through this thing here. So I've got 2 little propositions. So the moon is made of cheese. That's a proposition. It's either true or false. So it's a proposition. And then I've got this other little proposition, little q, winter is coming. So I could construct all kinds of arguments using logical operators combined in various ways out of these small propositions. So one particular argument, which happens to be valid, is this thing right here. The moon is made of cheese, or winter is coming, period. The moon is not made of cheese, period. Therefore, winter is coming, period. So the first compound proposition is the moon is made of cheese, or winter is coming. So we break up sentences. Basically, each sentence becomes a compound proposition. So this guy here is compound proposition P1, and it's made of little p, the moon is made of cheese, and then the logical operation or, and then little q, winter is coming. So symbolically it looks like right here it's P or Q symbolically, right? Then the second compound proposition is the second sentence. That's big P2, and it's the statement the moon is not made of cheese. So that's basically not little p. Okay, then the third sentence is the conclusion, marked by therefore, the word therefore, and it's just the little proposition winter's coming, which is just Q. So that's down in here. All right. So up here we have the argument in English, and then down in here we have the symbolic representation of the argument, expressed as compound proposition, expression, and another compound proposition, expression, another compound proposition, which is the conclusion, and then an expression. Okay, so what I did and what I'd like you to do is just dump all this stuff into a table, right? So here is that argument, that same argument broken up into a table so that we can check it for validity. So let's go through that. So we've got the little propositions P and Q, and we've got all 4 combinations of P and Q, 0, 0, 0, 1, 1, 0, 1, 1. Okay, then the remaining columns, we list the compound propositions. So there's big P1, big P2, and then Q. Big P1 is this expression P or Q. Big P2 is this expression not P. Big Q is this expression little q. And then we just fill this table out. So let's do that here just to walk through this thing. So here we're just applying OR to P and Q. So 0 OR 0 is 0. 0 OR 1 is 1. 1 OR 0 is 1. 1 or 1 is 1. Okay, that's where that comes from. And then not P is just the P column reverse. So 0 becomes a 1. 0 becomes a 1. 1 becomes a 0. 1 becomes a 0. That's that guy. And then Q is just the Q column over here, 0, 1, 0, 1, just copied over here, 0, 1, 0, 1. Okay, then, so we fill this table out. That's the first step. And then you do a check for validity. So what's the check for validity? The check for validity is you look at the compound propositions, just the big P's basically. In this case, P1 and P2. And you find the rows where the compound propositions are all ones. And those are the rows we're interested in. And then for each of those rows, you look at the conclusion. And if the big P's are true, then the conclusion must also be true. And that's the case on this row. So this is a valid argument. Because none of the other rows have all ones across there. Right? So we're only interested in checking the rows that have ones on for all the compound propositions. And for those rows, we check that the Q conclusion is also a 1. That's the condition for a valid argument. Okay, so what does this look like in the rest of the code? Now we can dump down in there. You can read this thing. Here I have another example where I have an argument that's it turns out to be invalid. It's invalid here because here I have 2 1s on the compound propositions, but the conclusion is not true for that. So this row makes the argument invalid. All right, but what did let's go through the implementation here. So let's see, I've got some pragmas. Yeah. Anyway, these are the prototypes. Some of these have been implemented already. I think I implemented not and or just to get this thing to run. And it runs. Here, I'll run it real quick for F5. So it spits out the argument that I've stored in a table, and it's telling you that it's valid. Well, right now, the code that I've given you is very conciliatory. That is, it just prints out every argument is valid because I want you to implement the is valid function. Okay, but anyway, this guy's valid, and yeah. All right, so I'm talking about the argument table here, which you've sort of gone through. It's just this format right here. And okay, so you need to know the number of little props and the number of big props, the capital P's and Q's, and then the lowercase P's and Q's, or PQ, could be R in there, PQRST if it was a big argument. I'm just calculating exponent to or base to the exponent, because here we have 2 little props. So we're going to have 4 rows because all the permutations of little p and little q gives us 4 rows, and that's given by the formula 2 to the 2, or once again 2 raised to the power number of propositions. So there's 2 little propositions, so it's 2 to the second power, or 4. All right, just basically all the permutations of P and Q, which is 2 to the power of number of little propositions. So that's how I'm using there here. I want you to write this is valid function. Right now, my version is very conciliatory. It just agrees with every argument and says every argument is valid. It's very easy to get along with program. Doesn't try and fight you. Print argument does just what it says, prints the arguments. Okay, here I've implemented OR because I'm using it in my code here. So this is the answer on how to do the previous homework that I gave you. So if you happen to look ahead, you might have found this, but this is the simplest way, I think, to implement any logical expression. Just put the output column as a hard-coded table, and then use the P and Q as an index into that table. Here I'm just shifting P over by one bit and then orient it with Q, and I get a binary number which gives me the index into this table. Very fast. A lot better than logic. Okay, anyway, here's not. All right, so in main, what I'm doing here is, let's back out a little bit here. All of this stuff in here is one argument. Okay, now I want you to repeat this code for all 6 of those arguments. That is, you could just copy and paste this code and then modify it to work for all 6 of those arguments. So it's not really that hard what I'm asking you to do. It's a lot of cut and paste and then changing some expressions. Just, you know, working with arguments, with code in kind of the most straightforward way that I could think of. I think the value of this is to get you thinking about how logic could be applied to code, because one of the uses of logic is, in theory, it could be used to validate the logical structure of your code to help reduce runtime logic errors. But that's a very new field in computer science, and it doesn't, you know, they haven't really made that much progress on it. But in theory, that's what you could do with this. All right, so I have to hard code some stuff. So the number of little propositions, it's 2. That's P and Q, that's 2. And then the number of big propositions, it's 3. That's P1, P2, and Q. That's 3. So that means there's going to be 4 rows, because there's 2 raised to the power number of little props. So there's going to be 4 rows. And this is just the iterator. I'm initializing row. And so we're going into a loop here, and we're looping through all 4 rows, row plus plus. And I'm using this bitwise trick thing to generate all the P and Q permutations. Okay, this will generate the 0001, 10011, all 4 permutations of P and Q. Then here I just hard coded the first compound proposition P1. Right? It's just P or Q. And then here I've hard coded the second compound proposition P2, which is just the expression not P. Right? And then I've hard coded the compound proposition big Q, which is also the conclusion and happens to be little q. Okay, so you'll have to change these as necessary for the additional arguments. Okay, pretty straightforward, right? Then just as you run through the rows here with the row plus plus thingy, just fill out the P, the columns, the P, little p column, the little q column, the big P1 column, the big P2 column, the q column. All right, pretty straightforward. Okay, then call is valid, which I haven't once again, my is valid is just a dummy. It just says everything's valid. But I want you to use this rule right here, right, to run through the rows and find the rows where all the premises are true. And for those rows, check if the conclusion is also true. And if that's not the case, then set a flag indicating that it's invalid. Or you could just return right away from that function, because you only need one row to invalidate the argument. So you could just break out of the loop and return invalid for that. Okay, pretty simple program here. Got some 2001 references in here, which I really think all computer science majors need to watch that movie if you haven't. It should be required to get the degree in computer science. It should be a degree requirement, in my opinion. All right, so one other thing, I'm talking about extra credit. I mentioned some extra credit for 2 pi points, so 3.1415 times 2, or 6.2 something points. All right, the real value of this thing, or that is, it would be more useful if you could enter these arguments in symbolic format at the command line. That would be nice. Okay, so right now I'm just asking you to hard code it, and that's all you need to do for the points. Is just this hard coded stuff right here. Just change that for every argument and do that 6 times for all 6 arguments. But it would be nicer if somebody could actually enter a string that looked like this P or Q string, and then have that evaluated by the program. that would make it a little bit more useful. So that's extra credit if you want to do that. Now how would you do that? Okay, how would you do that? There's a pretty sophisticated way that you could do it using a stack and a queue and parsing it. And that's pretty sophisticated. And you don't have to do that. You could, although that's the right way to do it, but an easier way to do that would just make a sort of a brute force table of strings and just find all the possibilities. You know, just look up this particular string, look up this P or Q string and return the answer for that. So that would be a big long if-else ladder or something with a bunch of string comps in it or something like that. You could probably get that to work. Like I say, there are more sophisticated ways to do that, but you know, give that a try. And you know, depending on how far you get, if you're interested in the extra credit, I might give you, you know, I'll give you 2 pi if you do it well, and maybe I'll give you more if you do a really nice job. Anyway, but that's about it. Okay, I think it's a pretty straightforward program. I'm just trying to, you know, give you something to do with code. Like I've mentioned earlier in this class, this is a discrete math class, but what value is that if we can't apply that to code? You know, we're here to learn, we're here to write code, not to have arguments and bars with people about whether the moon is made of cheese or not. So that's why I make you do these implementations. That's my attitude anyway. All right, have fun with that. Hope this was useful. See you next time. Bye-bye.